my last video, machine learning part 1 or whatever that's going to be, we learned about a specific algorithm called the perceptron, but we didn't really learn about it. I kind of glossed over it. 1957, Frank Rosenblatt created the perceptron. Yeah, that part of the video. We heard a little bit about that. But the perceptron is actually really important to understand because it is the foundation of neural networks, which is widely used in machine learning today. So if we're going to understand machine learning and train our own models, we kind of need to learn the perceptron. So that's why we're here today. We're going to understand the perceptron, how it works, look at a model of the perceptron, and then train our own perceptron model. That should give us the foundational building blocks of a neural network in machine learning so that when we move on to complex models, which we'll be using sklearn or scikit-learn to make, then we can understand how the models work, at least at an overview for some of these neural network models. There are different kinds of classifiers, different models, they work different ways, but with the basic foundation, you can kind of build on that. And that's the idea of machine learning. You're constantly building on the foundation, and that helps us to learn a lot better. All right, so bear with me here. How does a perceptron work? Well, we know that a perceptron was modeled after a biological neuron, meaning that a neuron takes in some kind of input, it runs it through some calculations and produces an output. In a biological sense, the output of a neuron is whether the neuron will fire off or not. So the perceptron kind of mimics that as well. It produces a binary output, 1 or 0. That easy, that simple. Although perceptrons do have variations, so there are things like multi-layer perceptron, we're only going to focus on the single layer perceptron, the most simple type of perceptron that exists. The idea of the perceptron, being modeled after the biological neuron, is that if multiple neurons come together, the strength of those neurons increase. In the same way, perceptron has something called a neural network in the perceptron algorithm, right? So you have multiple neurons, right, for this perceptron algorithm, and they come together and make the perceptron a lot better at what it does. An artificial neural network. That's pretty much what a perceptron is. Let's go one level deeper and understand how a perceptron works at a lower level. So first, you have inputs. We'll say 3. Usually, there's a lot that comes in at a time. For this example, we'll say 3. 3 inputs. They enter the perceptron. The perceptron then adds weight. 1 weight per input. So now you have 3 inputs, 3 weights. Those inputs and weights are sent over to something called a summation function. Yeah, that function pretty much just sums the input and weight, but it doesn't stop there. You see, the perceptron also adds something called bias. Brings down the bias, puts it into that summation function. So now we have inputs, weight, and bias. The inputs and weight are being multiplied together, and the bias is being added to the multiplied input and weight. So now we have our full summation function. Once we get the output of that function, it is then sent over to something called an activation function. This is where rules come into play. You see, the activation function says this: if the output of the summation function is less than or equal to 0, then the output value of the perceptron, which will be the prediction, we'll call that y prediction because y is going to be the variable that we'll use later on. So just bear with me here. That will be 0. So if it's less than or equal to 0, the activation function's output, y prediction is 0. If the activation output's value is greater than 0, then y prediction would be 1. Hence 0 and 1, the binary output. And that's relatively it. It's that simple. It's heavily used for classification, supervised learning. From the last video, supervised learning means that the data set has labels provided and it's more structured. Perceptron does that really well. Now, here's where things are going to get a little more complex. But bear with me because we're champions. We'll learn this. So let's take a step back. Before we dive a layer into the perceptron, we need to understand the biological neuron that the perceptron was modeled after. And we know that the neural network was pretty much started with the perceptron. So understanding the biological neuron will help us understand how the artificial neuron works, which then helps us to understand more complex neural networks, which ties into machine learning. See where I'm going with this? It all kind of links back together somehow. All right, let's dive into the biological neuron. We'll start there. Here it is. We have a biological neuron right before us. That's pretty much what the perceptron was modeled after. So let's walk through how this works from an artificial perspective, and then we can see what I mean by this was modeled after the biological neuron. So for starters, we have the dendrites, which are the very tip, looks like tree branches on the far left there. That's actually where the inputs will be coming in to the biological neuron. So inputs come into the dendrite. Then we have the soma, which is that space there right outside of the nucleus. That soma, we'll consider that our summation function. So that soma then does some kind of, we'll say math, right, for the input that's received. Then the output of that gets sent along the axon, which is that tunnel-like structure. Almost looks like a neck or something like that. It gets sent through the axon, right, and out through the axon terminals. And that's where we get our output, the 0 or 1. In this case, it would be whether the neuron is going to fire or not. Now, here's where things get more complex. So we just explained a neuron, but in a real neural network, a biological neural network, we actually have multiple neurons, a giant combination of neurons. So at the axon terminal, those little bulbs at the end, those are the axon tips. Those axon tips will eventually send data to another neuron through the dendrites, right? And that whole, the process in which that data is sent, it's sent through something called synapses, right? So synapses will then take the data, right, from the axon terminal, input data to a new neuron through the dendrites. That process is repeated. Then again, we have another neuron that will go and repeat that process again. Input, send it through the axon terminal, out the axon tips, synapse with another neuron, and that's how the neural network works biologically. Okay, seems simple enough, right? Let's look at a simple model of the perceptron and how it might be similar. Very similarly, we see a very simplified version of the perceptron. Let's walk through this. So we have inputs. In this case, we have our 3 inputs. They go through to the summation function. As they're being sent to the summation function, there's a weight applied to that input. In addition, we see the bias also being applied to the summation function. We'll see that formula a little bit later, but the summation function does its magic. Again, sends the data over through the axon tunnel, right? Through the activation function, we'll say the axon terminals, and then it gives an output, and that output would be either fire or no fire, 0 or 1. Then for the perceptron, right, we have our version of the synapse, because again, this is just one artificial neuron for the perceptron. In real life, the perceptron has several. So then it needs to send new inputs to another neuron, and that other neuron goes through the summation function, adds bias to it, sends along that axon terminal again to the activation function, and then produces another Y prediction. Simple, very simple still. Let's take one look deeper. It's going to involve a little bit of math, but bear with me because the math should be relatively simple. All right, now we have the same thing, a simple perceptron, but we just added math to it. That's pretty much it. Let's step through it and see if we can understand what's happening. So now our inputs are given variables. We say x1, x2, and x3. Our weight is also given variables, as well as our bias. The weight variables will say w1, w2, and w3, and the bias we'll say will be b in this example. So x1 goes through to the summation and bias function and is given a weight 1. In that function, we see wi, xi in the parentheses. That's the first thing that we see. So we need to note that the I here is technically equal to I plus 1, assuming that I starts with 0. So what we say is x1 is given a weight of w1 because I would be 1 there. Then we move to x2, I would be 2, and then given a weight of w2. So it's just a way to represent all the different inputs without having to have I being x1 for all of them. It could be x1 for all of them. I just think that for the sake of this model, it might be easier to show different inputs and different weights assigned to those inputs. So we say I equals I plus 1. Okay, so the input gets assigned a weight, added to the summation function, w1, x1, because that's what we're looking at. So wi, xi, those are multiplied together. So x1 and w1 are multiplied together. And then after those are multiplied, we have an addition of b. We add b to whatever the output of x1 and w1 is. Once we get that answer, we send it over to the activation function. As you can see, the activation function, if we were to graph it, looks like this. Actually, I don't know what type of shape that's called, but there is a name for it. I just I forget the name. But as you can see, it goes from 0 at the very bottom there to 1 at the very top. So whether we know the name or not, we know that this represents binary output, 0 and 1. So the activation function there is doing exactly what it should be doing, giving an output of 0 and 1. Now we see the rule that says 1, right? If the summation function, which is wx, so w times x plus b, if that value is greater than or equal to 0, that's 1. And it's 0 if the summation function, so w times x plus b, is less than 0. So it runs through the activation function, whatever the output would be, that would be your y predicted. In this case, we'll say it's greater than 0. So in this case, our output would be 1. Very simple. It's actually really simple to learn, not hard at all. Now that we understand the perceptron, how it works, let's go train our own model. Might as well. To actually make the perceptron with code, we're going to use a Jupyter notebook. Jupyter notebooks are usually used for machine learning to almost measure the training data output, analyze a lot of that information while the model's running. So it's a way to kind of analyze as you go, right? So really handy, really useful. Not everyone uses it. I certainly do recommend it for machine learning. So we're going to use it. I usually use a Jupyter notebook built into Visual Code, but that takes some setting up and I want this video to be relatively easy and for beginners. So for this, we're going to be using Google Colab, which you just go to Google Colab, start a new project, and it opens up just like this, just like how I see it here. Here, the only thing you'll probably need to know is your files, which in this case, I have nothing because I don't have it connected, but we can connect here and it'll connect once you open your files, and now it connects to your Google Drive. And that way you can save your file onto Google Drive and make edits as you wish. I'm going to actually rename this to Perceptron. There we go. Now we have our Perceptron IP Y and B. Okay, one quick thing about Google Colab is it loves to pre-fill in code. I'm not going to do that all the time. I may have it auto pre-filled depending on if it's the right thing. The big thing here is I want to explain what's happening versus just going through the motion and letting you follow along. So I may do that sometimes, I may not, but we'll see what Google Colab wants to do. And we'll just start coding the Perceptron based on how we modeled it. So first, we do want to add our import. We will use sklearn in the future, as sklearn takes our algorithms and it simplifies it. So all you have to do is call the algorithms from the sklearn library and it does all the math for you. Makes life really easy. We're going to use that later and see how it looks with the Perceptron later. But for now, we're going to do it manually, fortunately, because we're learning the Perceptron. And what better way to do it than a manual way? So the only thing I want to import right now is NumPy. So I'm actually going to import NumPy, and we're going to import it as NP, just like Google Colab wants us to. That's all. We don't need to import sklearn or any other thing. So what we want to do first is create our class, and the class is going to be called Perceptron. So this is the class that we're going to actually build our Perceptron model in. We actually want it like that. With every class in Python, we want to create what I call the init method. That's going to have every method in a class has self. This isn't really a Python kind of course, but I can absolutely explain some of these things if necessary. But just know that in init classes, you want self. And then for the machine learning model, the Perceptron, we want two things. We want the learning rate. So the learning rate is how quickly the model adjusts to its weights, and we'll set this to 0. We'll say 0. The other thing we want is the number of iterations for our model. So we'll say number of iterations, and that's going to be equal to, it doesn't matter, we can equal it to 1,000. So 1,000 iterations. We'll make that 100 just because it's a sample and we don't want to potentially run this forever, although I don't think we will. Okay, so now we want to create our variables within this function. So the first variable is, of course, we're going to do learning rate, and that's going to be equal to learning rate. Relatively easy. Spelled self wrong. There we go. Learning rate is equal to learning rate. I'm going to add a space so you can see the equal sign better. And then the number of iterations. So in iterations, and that's going to be equal to same thing in iterations. There you go. Okay, now for our Perceptron, we did have our inputs and we had our weights and our bias. The input we'll define later, but we do want to define our weights and our bias now. And we can set that to none. We can always change that later. So of weights, we'll put none, and self bias, we'll put none. So now our weights and bias are set. Now we need to create our activation function. Well, we need to create two things. We need to create our summation function, which is the function that takes the x1, which is the input, and the weights, and multiplies them together and then adds them to the bias. And then that function will then send the output into the activation function. And the activation function will then do the evaluation if it's 1 or 0, but as far as the output goes. So let's do the activation function first. And then when we set our summation function, we'll just send the output to the activation to make things easier, if that makes any sense. So we'll do activation function, and that's going to be self because it's inside a class, right? And so what we're going to put in there is our x input. So I want to call this something that's going to be easy to remember. So we'll say, I guess it will be the x input because we're taking our input, we're putting it through the summation function. So I guess we'll keep that as x input because it's still the input, and it will become output once it runs through the activation function. Here we just want to return np where. So basically saying you want to return np where something exists, right? So where the x input, so the input is greater than, because this was our activation function here. It was either greater than or equal to 0. If it was greater than or equal to 0, then the output's 1. Else, if it isn't, then the output will be 0. And as you can see, the condition, how it works, where true, yield x, otherwise yield y. So this is true, we yield 1, otherwise, that's basically how that works. Okay, now we got the activation function. We need to define what we call fit. Fit is going to actually have a number of things. It's going to have our weights, our bias, instantiated there. It's going to have our summation function. Then the summation function is going to send the data to the activation function. And then from there, there's one more thing that we want to add, and that's if the model gets the training data wrong. So in Perceptron, I mentioned that the model has a label that tells it if something is 1 or 0. So if the model sees the actual value being 1 but predicts the value being 0, that means that the model has incorrectly predicted on the training data, which is not something that we want. So we want the model to be able to update itself if it knows that it gets the training data wrong. That way, later when we actually test the model on test data, which is future data, the predictions will be more accurate. In this example, we're not going to actually test it on future data, but this is the idea. You want it to auto correct itself on the training data before you move on to testing. Okay, so of course we want to start with self because it's part of the class here. Now we need our input, of course, so we take our X input, and then this fit is actually going to give us our output. So that's part of the Y prediction from the model. So we'll just write Y predict as far as prediction, and that's going to be, we'll keep it as predict just for sake. Okay, so now we need to define our input shape. So the shape is going to be the X axis and the Y axis, we'll say. So that shape is going to be samples and then features. Features will be the columns, and then the samples are the feature. The samples are the different values in those columns, and that's going to be X bracket type input shape. There we go. So the shape of the X input, the columns and rows, that's what we're going to do. All right, now we need to set our weights. So we'll set our self weight, and it's set to none right now. We're going to actually set that to the NP say 0. So there's zeros in the features here. Boom. And we'll do the same thing with we'll set bias to 0. So set bias to 0. The weights is going to be set to the zeros that are in the feature. So there we go. Now we can set our training loop. So what I'll do here is just a little easier with comments. So we'll say find features and feature values. Weight and bias is fine, self-explanatory here. Weight and bias. This is our activation function, and we'll say where output is 1 if greater than or equal 0 and 0 if less than. That's for the activation. Okay, now for our training loop, and this is for the actual processing, so doing the math as I mentioned earlier. We'll run through this for, we won't really care about what that is for X or whatever. We're not going to use that later, so I'll just keep that underscore for Python. Self.in iteration, so we're going through each iteration, right? Iteration is basically saying run through the loop one time, run through the loop again, run through the loop again, and each time you run through, it's going to continuously train. So in our case, we're training 100 iterations, we'll say. All right, so now we need to iterate through the summation function and also the activation function, and then we'll also include error handling, make things a little easier. So for that, we're going to do for I is like, the summation function where we had I equals to I plus 1. So if it was, x1 or xi and wi as far as that formula there. So having that function be, if x was 1, then the weight would be 1. So xi, wi, having them multiply together and then adding that to b. That's the summation function. So that's why we use the I to define what that I would be. And then for the value here, we want x input. So we want x input of whatever I is. So if it's x1, then we want that x1. x2 is y is 2, then we want I is 2, then we want x2, so on and so forth. And then we want to enumerate, of course, all the values in x input in order to get those values. All right, so now we need to define what our summation function is, the output, summation function output, right? So that's a long variable. I don't recommend long variables in Python, but for the sake of this example and having super easy to read code, we're going to have it like that. So now what we want to do is we want to take those np dot, as you can see, dot product of two arrays, specifically if both A and B are 1D arrays, the inner product of vector without complex conjunction. So what it's doing here is it's multiplying the two arrays. That's pretty much all it's doing. It should give us an example so you can see it if you're still here. All right, so here's an example. So if np dot 3 comma 4 and that equals 12. So just multiply together and we get 12. So that's what we're doing for our function, which is exactly the same as this, xi times wi plus b. We could have written this a little differently. We could have done something like, we'll say x input I comma self dot, or x input I times self dot weight plus c. We could have done it that way, but why not do it the way with numpy since we already imported numpy? All right, so that's going to be x input I because we want the value that we're iterating through. We don't want to grab the whole thing or we're going to mess up the shape. And then we want to multiply that by the way. Since we're using numpy, we'll use numpy dot instead of just basic multiplication for this in this this case. And then of course we want to update that to the self bias, because the bias is what we're going to use to add at the end of this summation. All right, now we got the summation function, and I'll even put here summation function, and we got the output of that saved into a variable. We need to now add our activation function. So we're actually just sending an output of summation function to the activation function. That's all we're doing right here. So we'll call this y, we'll say predicted, because that was the output of the activation function, y predicted, and we'll set this to self.activation function. And that's going to be pulling from here, just activation function. So we need to define what the x input would be. In this case, x input is actually a little different now, because the x input is actually the output of the summation. So we're actually going to specify that, and it's going to send the value of the summation function into this x input so it can run this calculation. And there we go. We have our fit, and we're technically done, but we also should add some error checking. So if the model gets the training data wrong, as I mentioned, it should update itself. So to do that, we're going to just add a quick if statement. So if y predict, and we only want one value, we don't want all the values at once. So if only one value so far, because we're going to iterate through anyway. If it's not equal to, if the predicted is not equal to the actual, we're saying here, so y predicted, we want to do some kind of update. So I'll say error handling training data autocorrect itself for this case. All right, so in this case, we'll say the update part, we're going to update the learning rate, and we're going to multiply that by whatever that prediction is, because we're iterating through, and minus that by the actual. And so we're going to update the learning rate by that. Then we want to update our weights, self.weights, and that's going to be equal to self.weights plus update times the x input. So we'll just do plus equal to shorten this. That's going to be plus the update, what we just defined above, and that's going to be times x input I, which is the value of our iteration. All right. And then lastly, we want to update the bias. So the bias will be equal to its own self. So the bias plus update, and then that should change it. In this case, since the data set is going to be relatively small, binary value 0, 1, this is just changing it. If the prediction was 0 and the actual was 1, then the model will update itself to have the prediction to be 1. That's how that would work. Okay, so now we have our error handling. We can move on to the final step for our perception class, and that's to actually create the prediction function. We'll call that predict. That has self, of course, still part of the class, and we'll say x input. So it's going to take the input from the summation function and predict the output here. All right, so now we want to summation function output, right? We want to take that, we want to set it to, well, we want to multiply the input and the weights and the bias. So pretty much the same formula here, except we're not iterating. And this time we don't need to iterate because we have one input. So take input, and then we'll paste that right there. So weight and bias, there we go. So now we have the summation function output, and we want to run that through the activation function and return that. And that's going to be summation function output. There we go. So now we have our math set up with Python here. And the next steps, we just need to, well, first we need to set up our data set. And then from there, we need to actually run our data set through this math. So to set up our data set, we're just going to use basic OR, XOR for data set. So we'll say XOR data set. The reason why we're using an XOR is because it's binary output. An XOR is pretty much like a logical circuit that pretty much does like binary math. So if you have two binary inputs, 0 or 1, and you have a 1 in the equation, then the output's 1. Else, if there is no 1 in the equation, then the output's 0. So what that looks like is here. Let me write the data set, and I'll show you how that looks. So input is, we'll say NP array, and for this example, really small data set, I want to overcomplicate things. So that's going to be 0, 0 for the first one. Second one's going to be 0, 1. Third one's going to be 1, 0, and the fourth is going to be 1, there you go. All right, so there goes your input. It's set to that array. So the way that the XOR works is relatively simple. And the model, this is how the model is actually going to learn, because we need to set our labels anyway. So this is how we're going to set our labels for the model to learn. So if you have two binary inputs, 0 or 0, there is no 1 that exists. So that's going to stay 0. Now, if you have 0 or 1, and that's the second one here. So 0, 0 is the first, 0 or 1 is the second. Then there is a 1 there, so the output should be 1. The third is 1 or 0. So if you have 1 or 0, there's a 1. That's going to be 1. And the fourth, of course, is 1, 1. So if you have 1 or 1, then the output should be 1. And so if we have our label in this data set, this will be our label. A label for the first shape here, this is going to be 0. Second shape will be 1. Third shape will be 1. And fourth shape will be 1. So our model now knows the answers, the actual answers, and it should predict accordingly. So to do that, we're going to set our prediction based on this training data, and we're going to set the label. The label is yPredict. It's always going to be yPredict when you set your label in a data set. Even when we do a more complex data set, you'll see that we'll separate the label and we'll assign the label to a variable called yPredict. So just to make things easy. So in this case, we're just going to do it in an array. We're not going to use like a CSV or anything. We'll say 0, 1, 1, 1, make life easy. Okay, now that we have our data set, we need to actually initialize our Perceptron. It's relatively easy since we already created our Perceptron. All we have to do is give it a name, which we'll call Perceptron. We assign it to our class. That's all. We actually already created our learning rate in our in iterations. We already assigned them. We actually don't need to reassign them again. So all we have to do is just keep them empty here. If we want to change it, we can change it up here, or we can just assign it down here. We can do something like learning rate, and we can change that here. So we can play with it either way. All right, so now we can train the Perceptron with our data. So when we train, we actually call that fit, right? So we're fitting the data. So the fit actually comes from our fit class here. We're actually doing the math. That's all we're doing here. Perceptron, there we go. Perceptron fit, and we're going to fit that into our X input, and we'll also use our Y predict, because that's the output. There you go. Now we have our input, and so the input here, this is our data set, and this is the label, the output. So we're just going to train our data based on the label, and the model is going to know if it gets it wrong. It knows to go back and go through this error handle. So that's how that works here. All right, now that we have our predictions and everything, we can set our predictions to a variable prediction so that we can print it out and see the result. So we'll say Perceptron predict, and this is going to be X input. We're going to predict our input here, and then we'll print out our results. So in this case, we'll print out the prediction, and we'll call that predictions. Then, which is literally, we're assigning the prediction. We also want to print, here. We also want to print the actual values. So actuals, and then that's going to be set to the Y predict. So that's the actual output. And then lastly, Y predict is of course the math that we just did, the label. So it's going to be set to the label. And then lastly, we want to see our accuracy, to see how well the model successfully identified the classifications correctly. So for that, we'll say accuracy, and then that's going to be set to, we're going to have to define our own accuracy because we haven't defined it beforehand, but it's just going to be the means. So it's the mean of how many predictions were right. So how many times the predictions were actually equal to the actual value. That's what the accuracy is, and it takes the mean of that. So if all four predictions were correct, then the mean would be 4, right? So if all 4 predictions were wrong, then the accuracy would drop down, and that'll be 0.75. Sorry, if all were correct, the mean would be 1. If the accuracy dropped down, then all 4 to 3 correct out of 4, then that should be. And then I'll put here rinse outputs, just readability. Okay, so now we should be able to run our model that we just created. So we got our imports, we run our math checks out, no errors. Now we run our data set, checks out. We apply the data set to our math, we get an error. So support operand types for int none type, and that's in the summation function here. So that's probably np dot x input I self dot weights. Okay, so that's going to be in our fit function here. So we need to see what we actually did wrong, and summation function np dot but I self weights, that's right, self bias, that's right. So we need to look up and see where we actually so let's backtrack the fun part of code, I guess. Okay, so looking at self dot weights, see the error is basically saying unsupport operand type for int none type. So it's basically saying that self dot weights is pulling from none, which means that here when we initiate it, there it is. So we initiated self.weights, we actually had a typo in weights here. Weights with an S. There you go. And now when we run this, fix that. There you go. The actually correct. There we go. All right. So now when we rerun this, the weight should not have none type. It should have an integer, which is this. So typo in our variable happens to the best of us. All right, let's run this. All right, I forgot we actually need to run our function again because in memory, this typo still exists. Let's rerun this, rerun our data set again, and then we'll rerun. This time we get no error. That means it worked well. Now we can see our predictions. Okay, there we go. So the model predicted 0, 1, 1, 1. We expected that because if there was any errors, it would update itself and fix those. The actuals was 0, 1, 1, 1, and then the accuracy was 1, which because the predictions are all equal to the predicted. And if you take the mean of that, the mean is 1. So we have 100% accuracy, which is good. In this case, this is the training data. We would then go and give it test data. So when we're training the machine learning model, we have one big data set. We split that into training and test. This would be a training split, and then we would then test the model on the testing split and see how well it does on a test based on the training data or how it learned on the training data. In this case, we're not going to go through all that because the whole purpose was to see how the Perceptron works, and we see that how it works, and it accurately was able to train itself on the data that we gave it. In addition, we could also see how it looks on a graph. Well, let's see if we can add the perception decision boundary boundary graph we'll see, just to see how it looks, because we know that the perceptron is one layer, pretty much linear one layer algorithm, and so it's easy to represent that. For this, there is quite a bit of code, so I'm gonna actually pause the video. I'll type it out. I am going to import matplotlib, but I'll include this in a GitHub and I'll share that in the description. So if you want to take a look at the code, you can, by all means, feel free, and also play around with it. So matplotlib, there we go. And then this is going to allow us to be right back. Okay, back. Nice and easy, quick. So just really quickly, just going to run through this. Just setting up grid points here. I set the minimum value to, minus 0.5 and the max to 0.5 just to give more of a boundary for this. So the graph is going to start, instead of starting the graph at 0, it's going to start at minus 0.5 for the X value. And then for the Y value, also minus 0.5. And then the max, instead of stopping at 1, since that's our binary digit, it's going to add 0.5 to it. So it's going to be like from negative 0.5 to 1.5. Those are going to be the boundaries. Then I set up the mesh grid. The mesh grid is just, it's just a grid. That's all it is. I have that set to 0.02. I mean, I can change to 0.1. Doesn't really matter. And then this is to create that mesh grid that we just set. So setting the X, Y, Y values, and then we're creating the mesh grid with those values. And then from here, this is where we actually plot the boundary that we just created in the training points. And then from here, we can create labels as well. So the X value, we'll call that feature 1. And then the Y value, we'll call that feature 2. And then for the title, we'll just call that, again, with my typos, Perceptron decision boundary, right? And then we're going to plot that boundary with the input, the prediction, and then our perceptron class here. And then we're going to plot that. That's how you would kind of go through that. Plot is not defined. So we need to actually rerun our imports, I think. Yep. So we do need to rerun our imports. Let's try that. There we go. So after we run the imports, now we see that our perceptron decision boundary is made. This is again, one layer. So we only see one layer. There's a linear line that goes through that layer. That's expected. The perceptron is one layer and it is linear. Just a linear line that gets drawn through. And then we see the boundary points. The boundary points being our 4 points here from our data set. That being 0, 0, which is the purple one here. 0, 1, which is the yellow here. 1, 1, which is also this yellow one here. And then 1, 0, the yellow one here. And in ideal world, you're going to have a lot of training data, so you're going to have a lot of points all around. You're going to have this perceptron just having a linear line through all these points in its own boundary as you're reading how the perceptron is learning based on this trained data. And then you will go and have the test data, and you'll see results based on the test data as well. But for this case, this is how the perceptron actually works. Flat, super easy to go through. You're just running it through a function, and that's it. You just learn the perceptron, math behind it, the model behind it, and the code behind it. In the next machine learning video, we're going to go over sklearn, so you can see how easy it is to have these model algorithms generated with sklearn instead of doing it ourselves. And then we'll move on to the next steps. So at the end of this project, we're going to take a bigger data set. We're going to train several models with this data set, and we're going to analyze the model outputs. It'll be a fun thing. You might even be able to take what you learn here and apply it to, who knows, future technology. Maybe you can start detecting attacks. Maybe you can have models that will figure out what attacks go where, who knows. Thanks for watching. If you like this video, make sure you like the video. Comment. If you haven't subscribed, go ahead and subscribe. Let me know what you guys like to see as I dish out these machine learning based videos for this kind of project that I'm working on. I am going to be dishing out other videos on hacking, blue team defense stuff, maybe some GRC stuff. I might talk about what it's like to have a doctorate degree in cybersecurity. Maybe I'll talk about cybersecurity in the job field as well. So I'll have other videos coming out too, not just limited to this machine learning stuff. So make sure you stick around. And I have seen some suggestions. I love the suggestions I've seen so far. I will be making some videos on that. Things like analyzing PCAPs. I heard GraphQL part 3 that will be coming. Stick around, make sure you subscribe, and make sure you're tuned in. Doc out.